Faraday's Law of Induction. Michael Faraday and Joseph Henry separately showed that a changing current in one loop will induce an EMF in a second loop. The changing current in the first loop, what's that doing? That's creating a changing magnetic field. What is actually causing the EMF in the secondary loop is a changing magnetic flux, not just the changing magnetic field in the second loop. Faraday's law of induction states that the induced EMF in a wire loop is proportional to the rate of change of the magnetic flux through the loop. E, which is the EMF, is minus N. Don't worry about the minus, we'll get to that later. N is the number of loops you have. If you just have one loop, N is 1. But if you have a coil of wire and you have multiple loops, if you have like 20 loops, then you would put 20 in for that number. The more loops, the greater EMF. And here's your change in magnetic flux per time. Note it's not just the magnetic field, it's the flux that's the key here. Michael Faraday made some of the greatest contributions to physics in history, focusing on electricity and magnetism and how they interact with each other. Albert Einstein kept a picture of him along with pictures of Sir Isaac Newton, who we already know, and James Clerk Maxwell, who we will cover a little bit in electromagnetic radiation in his study. What's interesting about Faraday is he had only a basic education and no mathematical training beyond basic trigonometry. However, he had a fantastic vision and creativity and was a superb experimentalist. It remained for Maxwell, over here, to put a mathematical formalism behind Faraday's concepts. He created field theory. He applied it to electricity and magnetism, and then a version of that field theory was then used by physicists in the 20th century to describe quantum mechanics, to get into more detail on electricity and magnetism, all because of this gentleman in the 1800s. Let's look at each term in detail in this equation. Well, of course, E is the EMF that's created in the secondary coil. N is the number of loops, sometimes called turns of wire, in the second coil. Delta phi B is the change of the magnetic flux. Either the area of the loop exposed to the flux can change, or the magnitude of the magnetic field. Delta T, that's the time interval over which the flux is changing. The negative sign is related to the direction of the induced EMF, that is, which way the current will flow if it's a complete circuit, and that will be discussed later. For now, we're just going to worry about the magnitude of the induced EMF, and we'll work an example problem. Find the magnitude of the induced EMF in an 8-meter squared one-loop coil if it is perpendicular to a 0.40 T magnetic field that decreases to 0 Tesla over a time interval of 2 seconds. So we'll list our givens here. Here's our initial magnetic field, our final, our time interval, the cross-sectional area of the loop, and how many loops we have, which is 1. Your initial flux is B0 times A, and you get 3.2 Webers. Final flux is 0 because there's no magnetic field. So the change in flux, we always deal with final minus initial, will be a negative 3.2 Webers. But we're only interested in the magnitude of the EMF, so we're going to take the absolute value. We then plug in our various numbers. Here's our loop, here's our change in flux, here's the time, take the absolute value, and we get 1.6 volts is induced in the secondary loop, in the one loop coil there. We're going to do some algebra now for 2 reasons. One, it's fun, and the second, it'll drive home more critically what flux actually is. What if we have either the magnetic field or the cross-sectional area of the loop that's exposed to the magnetic field? What if either one of them is constant? Well, first, we're going to assume that the cross-sectional area doesn't change. So here's Faraday's law. We substitute in flux final minus flux initial for the delta flux, and then we define what each flux is. This would be B final, A final, minus B0, A0. Since the area of the loop doesn't change, we can replace A final and A0 just with A, because it's all the same. We put A in here for the AF and the A0. We factor out an A, And then we're left with the change in magnetic field over the change in time. So Faraday's equation changes to minus NA times delta B over delta T. A little more algebra. This time we're going to assume that the magnetic field is constant, but the cross-sectional area changes. Once again, start with Faraday, substitute in final flux minus initial flux, then put in the definitions of flux. Since our magnetic field doesn't change, we can replace B final and B initial just with B. That comes down here. We factor out a B, and then we have minus NB delta A over delta T.